Hey YouTube, what does the sun, space weather, and solar cycles have to do with the basic communications that we rely on every day as a species? Cell phones, radio, GPS, 5G. Stay tuned, find out.
So, if you're a living, breathing human in the year 2022, you know that we're hopelessly reliant on our technology. You know that we use it for communications. We use it for our appointments, for our finances, so that we don't get lost every day, figuratively and metaphorically. Our society as a whole also uses the same technology. Whether industry or transportation, the military, farming, communications, this all uses the same technology, which is essentially just a whole bunch of electromagnetic waves that are shot out through the atmosphere using towers and satellites, to put it very simply. These electromagnetic waves are modulated by atmospheric effects happening on our planet by Earth weather and by space weather as well. Now, we don't typically think of space weather and solar cycles as being something that we have to deal with when we do something as simple as make a cell phone call or use our phone's GPS. But actually, going back decades, amateur radio operators have had to use their knowledge of solar cycles and where we are on that cycle to use different frequency radio waves when trying to make a radio call to different parts of the world. This is back before the World Wide Web, when everything was a bit more manual. As a ham radio operator myself, I'm always very interested in some of the history behind this, and I'll explain that to you more in a minute here. Now, we usually think of the Earth as being an isolated bubble, but the truth of the matter couldn't be further from the case. Actually, amongst industry insiders in the satellite industry, there's been a noticeable culture shift in the past just couple years as awareness of space weather issues have grown. A commonly held view used to just be space is just a vacuum, but now if you bring that up at a meeting at one of these companies, you'll get laughed out of the room. So bringing this type of issue into the consciousness of normal people that aren't in the industry is worthwhile, I believe. Now, the primary driver of space weather in our little neck of the Milky Way is, of course, the sun. The sun goes through an 11-year solar cycle as its magnetic poles switch, and over the course of this cycle, it goes through what's termed maximas and minimas. There's a normal 11-year maxima and minima, and then there's larger periods over the course of multiple solar cycles. For example, we had a large maxima in the late 1900s, a few decades ago, and it's been winding down from that large maxima. The last few solar cycles were getting increasingly lesser and lesser, going into our current solar cycle 26, which seems to be about on par with solar cycle 25, the last one, which was very underwhelming. These solar cycles are measured by sunspot counts on the sun, and these have been measured since the 1600s. They actually had some funny ways of measuring them by having a light collect in a telescope and then shine onto a little piece of parchment, and they could spot little sunspots on it back in the 1600s. We have much more up-to-date versions of doing this now, of course, using satellites and different wavelengths and everything. But we still count to see how many sunspots appear on the sun, to see how active it is. How active the sun is predicts how many solar storms we're going to see. Now, during a solar maximum, the thermospheric temperature is increased twofold, And we see a lot more ultraviolet radiation, solar flares, coronal mass ejections, and coronal hole streams. Now, without going too into the weeds here, it's important that we familiarize ourselves with a few basic types of space weather. The first would be the solar flare, which is a big X-ray explosion that shoots off the sun and ionizes our atmosphere here on Earth. Next is going to be a coronal mass ejection, or CME, which is when a large plasma filament, and some of these plasma filaments are the length of 100 Earths lined up. These things are huge. This large plasma filament will bow off the sun and then break free and then create this shock wave that goes through the solar system. This will also cause geomagnetic storms on Earth. So next is going to be these coronal hole streams, which act as a sudden surge in the solar wind. And when you're looking at the sun, you just see this big black hole moving across the sun, much larger than sunspots. It's theorized that the interplanetary magnetic field, which is a direct magnetic coupling between the sun and the various planets, it actually goes into the sun at these points, and it's actually sucked the material out, and that's why they show up as black. These act like a sudden current surge to our geomagnetic shield and cause geomagnetic storms, which are then the last thing to touch on here. The geomagnetic storm is just whenever the Earth's magnetic field is compressed by the solar winds, and this will cause energy to go in at the poles and the equator and cause auroras. And if there's enough of it, it can actually cause a ground-induced current, which we'll talk about in a minute. So how do all these solar events interfere with our communications? Well, when it comes down to it, it's all just electromagnetic radiation at different vibrations that us humans use for all this technology. So here's an example of the frequency spectrum. As you can see, there's an inverse relationship between the frequency of the wave and how long it is. So shorter waves travel at a much higher frequency, and longer waves travel at a much lower frequency. This is because they all just travel at the speed of light anyways, so there's just an inverse relationship there. They're all going at the same speed, so you can fit more of the short waves in at that speed, so it has a higher frequency. As you can see here, the very lowest frequencies would be the Earth vibrating, the 7.83 hertz, that's the Schumann resonance. Then you have our AC power at 60 hertz. Then you have your AM, FM, ham radios, your smartphones, your cellular, your satellite, your Wi-Fi, your Bluetooth, radar. Then you get into microwave, infrared wave, heat, visible light, and then you get into the ionizing radiation, which is what the sun emits, that actually ionizes our ionosphere and creates all these communication disturbances. These are ultraviolet waves, which give you sunburn at the beach, X-rays, and gamma rays, which are only produced in the very strongest of solar flares. Here's an example of the radio spectrum zoomed in and how we in the United States have it partitioned between all these different little teeny tiny bands. So we break it up between extremely low frequency, super low frequency, ultra low frequency, very low frequency, very original, I know, low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, and extremely high frequency. And that pretty much covers the extremely low frequency will be the type of vibration that, for example, the Navy will use to communicate with submarines. And on the other side of the spectrum, the extremely high frequency would be like your 5G technology, millimeter waves. And in each of these bands is partitioned within hundreds of different sections. So you have amateur radio frequencies, you have various government organizations, you have different corporations buying leases on different bands in here. These are all regulated by the United States government, and you can get into some serious trouble if you're in a radio band that you're not supposed to be in. Now, based on the frequency that you're trying to send, they propagate differently through the atmosphere, and you have to keep that in mind while you're trying to send your signal. So if you're using a very low frequency, like for example, what the Navy uses to communicate with submarines, those just travel along the contours of the Earth. They hug the Earth. If you're using a skywave signal, which would be a lot of your amateur radio, AM, FM transmission, that actually bounces off the ionosphere and then skips a few times before it ends up at its final destination. The next is your troposcatter, which would be in your VHF and UHF bands, which basically just means that there's some kind of turbulence in the atmosphere, which is scattering these around a bit so that these waves spread out further and reach more targets. The last one, and in your UHF and SHF bands, would be traveling by line of sight. This would be like satellite communications and 5G millimeter waves. Very high frequency, you can pack a lot of information in them, but they don't really bounce off stuff, so you have to have, a repeater every few blocks, which is how 5G works. Radio operators have known for a while that frequencies below 14 megahertz, which is about in the middle of that skywave section there, travel better at solar minima, and above 14 megahertz better at solar maxima. So based on where you are in the solar cycles, whole radio bands go in and out of operation. It's actually quite fascinating. And this is based on the excitation of the ionosphere. The ionosphere has a few different layers to it, and we call them the D layer, the E layer, the F1 layer, and the F2 layer. Actually, at night, it's just D, E, and F, but during the day, the F layer splits into 2 layers, and they all ionize differently, so different frequencies reach different layers of the ionosphere before it didn't bounce back onto Earth. A deep knowledge of how these ionospheric layers operate is what allows skilled radio operators to send signals across the world without using any repeaters along the way. They just are able to bounce it through the ionosphere and reach people across the world. These layers extend further out towards the sun during daylight hours. And during these daylight hours, the D layer, the lowest ionosphere layer, will actually absorb a lot of these low frequency waves that propagate well otherwise. However, when the D layer is absorbing these low frequency waves, it is actually letting some of these higher frequency waves bounce off of it. So you can switch to a higher frequency. Something more like a cell phone will actually bounce off the ionized atmosphere better. And when you have a geomagnetic storm or you get crazy auroras, you can actually bounce UHF, ultra high frequency waves off of that. Now, historically, for the last 100 years or so, radio has been how we as a species do all of our communications, going back to when Tesla and Marconi were inventing it. Recently, in the last few decades, undersea and underground cables and the internet have been replacing a lot of this communication that was previously done with radio. Now, in some situations, radio is still preferred. For example, airplanes still use radio when they travel long distances. If an airplane is just going over a city or something, it's actually just sending its signals down to little repeaters on the surface. But if an aircraft is traveling a long distance or going over an ocean or large body of water, it's traveling via radio, being bounced off the ionosphere. So these radio operators still need to know how that's done. And it's especially important, actually, Canada has poured a ton of research into this. Canada and Russia have both poured tons of research into this because they are the most vulnerable to geomagnetic storms, and so they need to know how to communicate their aircraft during these storms. And then, of course, beyond aircraft and the radio that you listen to in your car, a lot of amateurs still use radio, myself included, and they're very big with preparedness minded folk because it's a reliable form of communication even if everything else goes down. You can still always rely on bouncing radio waves off the ionosphere, so it's always something good to know about. Next, we might ask ourselves how cell phones work, considering that they're the little gadget that we're most addicted to. Cell phones work in the UHF band of the radio spectrum, so they're at a very high frequency portion of those radio waves. Because they're so high frequency, you can't bounce them off the ionosphere unless there's a crazy geomagnetic storm going on. They're always going to go through the ionosphere. They're just going to go right out into space and get lost. So because of that, we use line of sight communication between cell phone towers. The average phone can reach a cell phone tower about 22 miles away. So you see these things paced every few miles so that people can constantly reach cell phone towers. And these cell phone towers are connected underground through underground internet cables and undersea internet cables. And because of that, it's a very shielded form of communication. If you do run into some space weather events, cell phones are going to be one of the best forms of communication so long as the power grid is still working, which we will touch on ground-induced currents in a minute. 5G is the new thing. 5G is the new trend that everyone's talking about. Those are extremely high-frequency radio waves in the millimeter band, and those will be even more so. There's no way those are going to be affected by space weather. The only thing that will affect it is through losing power. The only way that cell phone and 5G waves would be interfered with would be through very low troposphere moisture, because the moisture actually does absorb and reflect these very high frequency waves. I don't know, maybe you've noticed that on a very foggy day, your cell phone reception still works, but it's not 100% there. This would be kind of a similar deal. There is research showing that during solar minima, there's a weaker magnetic field around the whole solar system. And because of this weaker solar field, more galactic cosmic rays are able to penetrate Earth's atmosphere. And those galactic cosmic rays seed clouds and lead to periods of higher moisture. So there is research showing that, but it'd be such a small effect on cell phone communications, I would not worry about it. So now let's get into something that is affected by space weather, and that would be satellites, data satellites, and internet satellites. And for this example, I wanted to kind of focus on Starlink. We're constantly seeing news stories about Starlink and how it's being used in the Ukraine, for example, and basically powering the whole war effort over there. Now, Starlink operates in the millimeter wave band, about the same as 5G. It's an EHF, extremely high frequency radio wave, and for the most part, it's going to be unaffected by ionization of the atmosphere, but it will be affected by water in the atmosphere. This is a phenomenon known as rain fade, and it affects satellite waves during rain, fog, snow, and moving through clouds. And so what they've done on these satellites, and this is something that Starlink has done too, is they have algorithms that map the weather, and based on the weather, these algorithms try to compensate by increasing the strength of these radio waves based on what kind of weather they're moving through. But more extreme storms sometimes cause issues there. I mean, like my last video was about all the water that was released from the Tonga eruption that increased the water content of the stratosphere by 10%. So that's an extra 10% of water disruption that all these Starlink satellite waves have to go through. Something to think about. So in February of 2022, SpaceX lost 40 out of 49 satellites they shot up into orbit. And this was because they shot them into orbit during a geomagnetic storm and thought they could do it, but miscalculated. The reason that these 40 satellites went down was due to a phenomenon called atmospheric drag, which increases substantially during geomagnetic storms. This atmospheric drag happens when the ionization of the atmosphere increases the temperature and density of all the molecules there that the satellite is trying to move against. And based on the resistance that the satellite experiences, it'll get lower and lower in its orbit until it reaches a critical altitude, in which case it just starts spiraling back down. And so 40 of these satellites were not able to reach their main orbit. Now, it's not just a phenomenon when you're shooting satellites up for the first time, but satellites that are already established in their orbits deal with this as their primary source of failure. To give you an example of how serious of a phenomenon this is, under solar minima conditions, a satellite can last for about 30 years when the sun isn't doing too much. Now, under solar maxima conditions, satellites can only last about 3 years when the sun is constantly shooting off coronal hole streams and solar flares and coronal mass ejections. Satellites can't last that long because the atmosphere ends up pulling them down. Now, GPS is something where I think it'll hit us pretty hard if something ever did go down. I don't know about you guys, but when I'm out driving nowadays, I am pretty much exclusively reliant on GPS to find places. I don't typically check road maps anymore, and I find myself getting lost pretty easily if my phone is dead and I can't rely on GPS. Beyond just average humans trying to find their way around town, GPS also controls a lot of automated tasks, such as farming, maritime, military, self-driving vehicles. GPS controls a lot of how our society actually operates. Now, how does GPS operate? GPS operates at 1.2 and 1.5 gigahertz, these two frequencies, which are in the UHF portion of the radio frequency band. This is a similar frequency level to that used by cell phones. Although the difference here is while cell phones are going in between towers and then into the earth through internet cables, these waves are being sent between satellites and everyone on the earth. So these ones are a lot more vulnerable towards space weather and atmospheric phenomena. The first way that GPS can be interfered with is just that now the sun actually outputs the same frequencies that GPS uses in the 1.2, 1.5 gigahertz bands. The sun actually emits those same frequencies. So if the sun is going through a storm and emitting a lot more of those frequencies, that can interfere with the satellites. And the ionization of the atmosphere also interferes with them. Now, the reason that GPS still typically works during a lot of these weather events is that there's a lot of computers on board that compensate for these attenuating effects and are able to cancel them out. There's also a phenomenon called dual frequency operation, in which case the GPS uses both 1.2 and 1.5 gigahertz. It doesn't just pick one or the other. Our phones just pick one or the other, so if there was a bad solar storm, Our phones would probably go down, but a lot of the automated farm machinery and stuff uses this dual frequency operation. Now, where things get crazy with GPS is this phenomenon known as scintillation. What scintillation is a phenomenon where these pockets of plasma get dislodged from heavily ionized parts of the ionosphere, magnetosphere, where they're interacting with the interplanetary magnetic field reaching out to the sun. And where this interplanetary magnetic field hits the Earth, we have these rings and these solid areas of ionized plasma. Now, as this moves around throughout the day, these solid portions of plasma break off and create all these little pockets of plasma that then diffuse into the atmosphere. And as a species, we have not found a reliable way to predict where these little pockets of ionized plasma are going to end up. These actually cause GPS loss. It increases the phase and the amplitude of these UHF waves and causes phones and even dual frequency operation to lose its GPS lock and not know where it is. Which, alright, so you lose your GPS lock a little bit, big deal, whatever. Well, when you have like automated aircraft and stuff that are heavily reliant on this, then that suddenly does cause a serious issue and potential danger to human life. These little ionized pockets of plasma are typically during normal times just around the high latitude regions, and also there's an area where a lot of these little pockets of plasma trail along behind the nighttime line around the Earth. But they're always around the high latitude polar regions, so places like Canada and Russia and Scandinavia have spent a lot of resources studying them because they have a lot of issues with GPS in those countries. These are highly correlated to the 11-year solar cycle, as in there is way more of these plasma pockets during solar maximum and way more GPS scintillation during the middle of these solar cycles. Now, the last thing we have to watch out for when it comes to how the sun affects our grid here on Earth is going to be through the formation of ground-induced currents. Now, these are currents that are created through induction, which is when two electrical surfaces share the same magnetic field, and a current in one surface creates a current in the other one. This is how wireless phone chargers work, for example. But when you have a large electrical current being formed in the ionosphere during a geomagnetic storm, it can create currents on the Earth's surface. And these are typically created through metal conductive surfaces like pipelines and power lines and railroad tracks, and also transformers. Electrical transformers are actually major failure points during these events and can cause the grid to go down. This happened in the past during the 1895 Carrington event, which is a very commonly cited example of extreme space weather. This was a large coronal mass ejection that knocked out telegraph wires all over the US and Europe, caused sparks to come out, and this was through a ground-induced current. A similar event happened in 1989 called the Quebec Blackout, when all the power in Quebec went out for a period of about 12 hours. They were able to bring it back pretty quick. But what happened is during a solar storm, some of their transformers shorted out because they caught a ground-induced current from induction from the atmosphere. Most recently, in 2012, there was a CME that missed the Earth by about 1 week. Physicists believe that this would have been a second Carrington event if the Earth was 1 week forward in its journey. So just to show you as an example of these things are flying around us all the time, we get lucky most of the time, so we don't have to deal with them. but there may come a time where we do have to deal with them. Now, how this would play out is it wouldn't exactly affect communications per se, but it would make these transformers go crazy and all these relay switches and everything all short circuit, and the whole power grid would just go down. So you could operate through backup batteries for a while, but there's only so long the cell phone towers are going to work for. Now, the last thing I'll mention here is something that hardly anyone's been talking about. A couple other channels have. Ben at Suspicious Observers has been one who's been trying to raise awareness to this. But the magnetic poles have been moving at an accelerated pace the last few decades. During the mid-90s, these magnetic poles were moving at about 9 miles per year. And now here, in 2020, they were moving at 34 miles per year. So that's a rapid acceleration there. And the field strength is also decreasing rapidly. Overall, and in very specific areas too, there's a large bubble in the South Atlantic Ocean called the South Atlantic Anomaly, where magnetic field strength is dropping precipitously. Actually, there was a recent storm on December 14th of 2022 where there was several solar flares that shut off, low-grade solar flares, just M-class, which typically just, bounce off our shield. They don't cause any damage. But these M-class, M2, M3, and an M6 storm, flare, they created the storm in the South Atlantic where they hit. They hit directly over that weak spot in the South Atlantic anomaly, and it caused a blackout over the South Atlantic. That was over an ocean, but if it was over, mainland area, that could be a much different issue there. The main data set that's used to map out our magnetic field and how that's been moving is known as the World Magnetic Model, or WMM. And this is released every 5 years for the use by industry leaders in aviation and the satellite industry and anyone that could possibly need this information. In 2019, they actually had to release this model a whole year early because the 2015 version was so out of date because of how fast the poles were moving and how much the field was weakening. They couldn't last another year to make it to their scheduled 2020 release because planes were having issues landing and navigating. So because of that, they had to release it a whole year early, and that's never happened before. So give you a little idea there. So moving forward, we can expect weaker storms to cause an increased amount of damage to the grid just because our protective shield is losing steam. Something to make you aware of there, and that pretty much covers all of the different ways that space weather and solar cycles interfere with our communications here as humans. There's a lot of different ways it can happen. A lot of people don't know about this stuff. You could surprise some friends at fancy dinner parties with this kind of trivia. Who knows? Maybe you'll invent something. To lead you out here, I'm just going to play a little track from the Danish Space Agency, where they actually took the sound of our magnetic field holding off a solar storm, and they converted it to audio. So give it a listen here, and I'll see you guys next time.